Hi, I'm Cody Jackson for Raft. This video will discuss and demonstrate how Raft's Hardware in the Loop project can be used to test software before it is deployed to a hardware device. Hardware in the Loop, or HIL, is designed to provide a software framework to allow developers to deploy code to a software simulation of a real-world hardware device. This allows them to validate the code before deploying to the hardware, thus reducing errors in troubleshooting. CLI is a framework to reduce deployment and destruction of various software constructs. In this demo, it's going to be used to create a Kubernetes cluster. Briefly, the HIL workflow starts with a code repository. When new code is pulled from the repository, an operator Docker image is deployed to a controller device to handle the rest of the pipeline. The code is checked to see if it fits a list of accepted hardware devices. If not, the pipeline fails. Otherwise, the code is used to create a Docker image that is deployed to a Kubernetes worker. At this point, the code can be utilized in a simulation setting for validation. When ready, the code is deployed to the actual hardware device and checked for success. For this demo, we will be using a Tello drone, which is a low-cost drone that's often used in education. One benefit of the Tello is that it has a Python API, which allows scripting of a flight path. A simulator program is available to test the scripted flight path prior to deployment to the drone. Since the simulator is based on Jupyter notebooks, the parameters can be modified and immediately checked. The simulator not only shows the textual results of the commands, but can also show the projected flight path via graphical plots. For drone use, a Kubernetes cluster is created via the Raft CLI with access provided to the Hardware in the Loop program. When HIL is executed, the operator image is deployed and the payload Docker image is built and pushed to the local host. One of the Kubernetes pods is labeled for use with the payload, and that payload image is deployed to the pod. The cluster is configured for port forwarding, and the URL for the Jupyter notebook is used to open the notebook. Once the Jupyter notebook is opened in a browser, the drone simulation is started. The necessary packages are imported and an instance of the simulator is created. Once a simulated drone is created, it is set to take off. At this point, the simulator provides output about the drone's altitude and, later, its position. We increase the altitude of the drone from its takeoff height. The simulator displays this change in a vertical height plot. Next, we turn the drone in preparation for horizontal movement. After turning, the drone moves forward 30 centimeters. This movement is displayed in a horizontal plot. After moving forward, the drone is told to descend slightly. As shown, projected drone movement is tracked. Both the vertical and horizontal plots are continuous. Each change in position is maintained in memory, so all changes are reflected in subsequent plots. After descending, the drone is turned around and moved back to its launching location. When commanded to land, the simulation program provides a review of the horizontal and vertical plots of the planned flight. When completed, we can save the Python code into a JSON file and then later recall that JSON file via the load command, and the program will execute all of those JSON commands as Python code and redisplay everything that we went through manually. It will do it programmatically. When the code is deployed to the drone, the simulator will show you the responses that are coming back from the drone, letting you know whether the command was successful or it failed. This video shows the previous commands being sent to the drone. Each command is processed before being sent to the drone, thus the slight hesitation in movement. You'll notice that the drone failed to return to its original starting position. This demonstrates how reality may not match simulation and why this drone is popular for educational purposes. This is not indicative of the Hardware in the Loop project, but is due to the drone. This demonstration does show that Hardware in the Loop can be used to deploy software to a hardware device via Kubernetes clusters and Docker images.